Right now, there is a spacecraft on its way to Jupiter, and this December it is coming back here first. Europa Clipper left Earth in October 2024, flew inward to Mars, turned around, and on the 1st of December it passes this planet again, because the only affordable route to Jupiter runs 2.9 billion kilometers to close a gap of 600 million. That is the true shape of every journey out there, and it gets worse the closer you look. 8 years and 9 billion kilometers to reach Mercury, the planet next door. 900 days for a Mars mission, 500 of them standing still, because nobody can leave early. 1.8 millisieverts a day coming through the hull, every day, in both directions. 12 years to Neptune, for a single afternoon. By the end of tonight, you will know exactly what the crossing takes and who actually ends up paying it. Get comfortable. If you are the kind of person who enjoys finding out that the easy part was never the part you were told about, a quick like and subscribe helps this channel reach more curious minds like you. Because by the end of this, the word journey is going to mean something rather different. Now, let's gently drift into this. Somewhere in the room with you there is a flat surface. A table, a desk, the arm of a chair, the floor beside the bed. Put your hand on it for a moment, if your hand is free. Feel how still it is. Feel how completely it agrees to stay where you left it. That stillness is the reason almost everything you believe about traveling between planets is wrong. And I want to spend the next 2 hours taking that belief apart very slowly, in the dark, with you, without ever once raising my voice. Here is the picture most people carry. There is a diagram, you have seen it 100 times, on a classroom wall, on the side of a cereal box, in the opening seconds of a documentary. A yellow circle on the left. Then a row of colored dots getting steadily further apart as they march to the right. And between the dots, sometimes, a little dotted line with an arrow on it, showing the path a spacecraft takes from one to the next. Earth to Mars. A dotted line and an arrow. That line does not exist. Not approximately, not as a simplification, not as a useful first draft that gets refined later. It does not exist at all, and nothing has ever flown along it, and nothing ever will. The diagram on the classroom wall is not a rough version of the truth. It is a different shape entirely, and the difference between the two shapes is where every frightening thing in this video lives. So stay where you are. Keep your hand on that flat, obedient surface, because I am about to take it away from you. You are not sitting still. You know this, in the abstract, the way you know your blood is moving. The room around you is turning with the planet, which is carrying you eastward at a speed that depends on where you happen to live, a few hundred meters every second if you are somewhere temperate. But that is the small motion, and it is not the one that matters tonight. Underneath it, and much larger, the whole planet is falling around the sun at roughly 30 kilometers every second. Not 30 kilometers an hour. 30 kilometers in the time it takes to say the word 30. You have that speed right now. You have had it your entire life. It was given to you before you were born, and you will never be asked to give it back. And this is the single most important thing to understand about leaving Earth, because when a rocket lifts off, that speed comes with it. This is where the diagram starts to fall apart. A launch does not begin from rest. A launch begins from a platform that is already moving faster than any bullet ever fired in a direction the crew did not choose, and the engine, for all its noise and fire, and the way the ground shakes for kilometers around, changes that speed only a little. The rocket is not a vehicle setting out on a journey. The rocket is a small nudge applied to something already in flight. And after the nudge, the engine stops. That is the part nobody puts in the diagram. The burn lasts minutes. The journey lasts years. For all but a few moments of an interplanetary crossing, nothing is thrusting, nothing is steering, nothing is powered. The spacecraft is simply falling in a long curved arc determined entirely by the sun, the way a thrown stone falls in a long curved arc determined entirely by the Earth. You do not drive to Mars. You throw yourself at the sun with tremendous precision and miss, and Mars happens to be in the place where you come back up. Sit with that for a second, because it changes what kind of thing a journey is. Let me show you what the real shape looks like, using something that is happening right now while you are lying there. There is a spacecraft called Europa Clipper. It is the largest machine of its kind ever built, with solar wings that span about 30 meters, roughly the width of a basketball court, and it left Earth on the 14th of October, 2024, bound for Jupiter. Jupiter, at its closest, sits about 600 million kilometers from us. Where do you imagine it is now, most of 2 years later? Most of the way there, presumably. Somewhere out past Mars, in the dark, closing the gap. It is coming back. On the 1st of December this year, about 4 months from tonight, Europa Clipper will pass close by the Earth. Not near it in the way that deep space objects are sometimes loosely described as near. Close. It will come back to the planet it left, swing past, and steal a little of Earth's orbital motion for itself on the way through. It has already done something similar at Mars, on the 1st of March, 2025, when it dived inward, the wrong direction, entirely, to borrow speed from a planet on the way to a completely different one. And after all of that, it will arrive at Jupiter on the 11th of April, 2030. 5.5 years, in total, to cross 600 million kilometers. The distance it will actually fly along the way is about 2.9 billion. Do you see the ratio there? Roughly 5 kilometers traveled for every 1 kilometer of separation closed. If you drove your car like that, a trip to a town 20 minutes away would take you an hour and a half, and would begin by driving in the opposite direction for half of it. And here is the part that should genuinely change something in your head, that is not the wasteful option. That is the cheap one. That looping, doubling back, inward, then outward path is the least expensive way anyone has ever found to put that much mass into orbit around Jupiter. The straight line, the dotted arrow on the classroom diagram, would require an amount of fuel that has never existed on any launch vehicle ever constructed by our species. Not would be difficult, would require a rocket that is not possible to build. So the detour is not a compromise. The detour is the only door. There is a reason the loops help, and it is a lovely one. A rocket engine fired while a spacecraft is moving quickly, deep inside a planet's gravity, converts its fuel into useful speed far more effectively than the same engine fired slowly, far out in the quiet. So, a spacecraft dives toward a world, fires briefly at the bottom of the dive, and comes out the other side richer than the fuel alone should have made it. Falling first, then burning, is worth more than burning on its own. The universe gives a discount to anything patient enough to fall. And there is a second reason, which is simply arithmetic about borrowing. When a spacecraft swings past a planet and comes away faster, that speed was not created. It was taken out of the planet's own motion around the sun. Europa Clipper will leave here in December with a fraction more energy than it arrived with, and the Earth will have a fraction less, and the books balance exactly. The amount taken from the Earth is so small that no instrument will ever find it. But it was taken, and the planet paid it. I want you to picture it properly, because the numbers slide off the mind and pictures do not. Imagine the solar system laid out on the long table in front of you. The sun is a grapefruit at the far end, warm under a lamp. Earth is a grain of salt, about 10 meters away the length of a large room. Mars is another grain, a little further. Jupiter is a marble at 50 meters, out the door and down the hallway. And you are standing beside the grain of salt that is Earth, and you want to reach the marble. Reach out. Your arm is long enough to cross a meter of that table, maybe 2. And it will not help you at all, because nothing on this table is sitting still. The grapefruit is fixed, but every grain and marble is sliding along its own circle, each at its own speed, and you cannot simply place your hand on the marble, because by the time your hand arrives, the marble has gone. You are not reaching for an object. You are reaching for an appointment. You have to let go of the table entirely. Throw yourself along a curve that begins by going toward the grapefruit and aim not at the marble, but at an empty patch of tablecloth where the marble is going to be in 5.5 years. That is the maneuver. Every time. For every world. And there is one more thing about that table, and it is the thing this whole video is really about. There is a price for the throw. There always is. Something gets spent on every crossing, and here is what almost nobody realizes. The price is not distance. Distance is free. Distance is the part that costs nothing, because once you are falling, you fall for as long as you like, and the falling does not charge you anything. Something else is being spent. At every single world in this solar system, something different and specific is taken from whatever makes the crossing, and it is never given back. At the nearest planet, it is energy, and it is far more energy than you would ever guess. At the friendliest planet, it is the arrival itself. At Mars, it is your ability to change your mind. Further out, it is cells in a body that will not replace them. Further still, it is electronics and warmth and light, and finally something so scarce that the entire output of a nation is measured in a quantity you could hold in one hand. And every one of those payments, without exception, converts into the same underlying currency at the end. We are going to walk outward tonight, one world at a time, and collect them. But we start with the world that breaks the diagram hardest, the one that is closer to you, on average, than any other planet in the sky, and that has been visited by exactly 2 machines in the whole history of the species. There is a machine falling toward the sun tonight that has been falling for almost 8 years. It is about the size of a small van. It is painted in white and gold thermal blankets that have been slowly baking for the whole of that time, and it is called Bepi Colombo, and it is going to Mercury. It left Earth on the 20th of October, 2018. If you cast your mind back to what your life looked like in the autumn of 2018, where you were living, who you were seeing, what you were worried about, that machine has been in flight for all of it, without stopping, without landing, without arriving anywhere. And in about 100 days, it finally will. On the 21st of November, 2026, Bepi Colombo is scheduled to slip into orbit around Mercury and become only the 2nd spacecraft in the history of our species ever to do so. The 2nd, ever. Around the planet that is, on average, closer to the Earth than any other planet in the sky. I want to make sure that lands properly, because it sounds like it must be a mistake. People generally assume Venus is our nearest neighbor, and at its closest approach, Venus does come nearer to us than anything else, about 38 million kilometers. But closest approach is a moment, and moments are not where anyone lives. If you take the honest measure, the average distance between the Earth and each planet, worked out across the whole cycle of their orbits, all the near passes and all the far ones together, the winner is Mercury. Because it hugs the Sun so tightly, it never gets very far from us. It is our most consistent neighbor. It is almost always somewhere in the region of 100 million kilometers away, which, by planetary standards, is next door. And it is one of the most expensive places in the entire solar system to reach. Here is why, and it comes straight out of the thing I put your hand on at the start. You have 30 kilometers per second. Earth has it, you have it, the launch pad has it, the rocket sitting on the launch pad has it. That speed is the reason we do not fall into the Sun. It is a permanent sideways sprint, and the whole planet has been sustaining it for 4.5 billion years. Now suppose you want to go inward. Suppose you want to get down to where Mercury is, close in against the furnace. What has to happen? You have to slow down. That is the whole problem in one sentence. To fall toward the Sun, you have to shed a large part of that 30 km per second sideways motion. Because as long as you are sprinting sideways that fast, you keep missing. And in space, slowing down costs exactly what speeding up costs. There is no friction to help. There is no atmosphere to lean into. No brakes. No hill to coast up. Every kilometer per second you want to lose has to be paid for by throwing mass out the back of the vehicle in the opposite direction, exactly as if you were trying to gain it. This is the sentence I would like you to carry out of tonight, if you carry only one. In space, there is no downhill. Falling toward the Sun is climbing. It is climbing in the only sense that matters, which is the sense that costs fuel. The numbers on that are startling. The energy required to reach Mercury is commonly quoted as around 8 times the energy required to reach Mars. And the amount of velocity change needed to actually enter orbit around Mercury, not fly past it, but stop there, is in the same range as the amount needed to reach Jupiter. Read that again slowly, because it is one of the strangest facts in space travel. The smallest planet, the closest one, the one tucked in against the Sun, costs about the same to arrive at as the largest planet in the solar system, sitting 700 million kilometers out in the other direction. The solar system is not a line with cheap seats at the near end. It is a bowl. You are sitting on the rim. Everything is uphill from here, in both directions, and the inward slope is the steeper one. So how do you reach a place you cannot afford to reach? You do what Europa Clipper does, but far more of it. Bepi Colombo's route uses 9 separate planetary flybys. 1 at Earth, 2 at Venus, and then 6 at Mercury itself, each one a carefully aimed pass that bleeds away a little more speed, dropping the spacecraft's orbit closer and closer to the planets, until the two are finally slow enough relative to each other that a modest engine burn can lock them together. 6 passes at your destination before you are allowed to stop there. Imagine driving past your own house 6 times over 4 years, each time a little slower, before you are finally moving gently enough to pull into the driveway. The total distance flown over that campaign is around 9 billion kilometers. The gap it is closing is, at its narrowest, about 77 million. That is a ratio of well over 100 to 1. 9 billion kilometers of falling, looping, and bleeding off speed to arrive at the planet next door. And the machine is doing all of this with an engine that produces almost no thrust at all. Bepi Colombo's transfer module runs on electric propulsion ion thrusters, which accelerate charged atoms out the back at enormous speeds, but in absurdly small quantities. The push is roughly comparable to the weight of a sheet of paper resting on the palm of your hand. You would not feel it. You would not be able to tell whether it was on. But it can run for months at a time without stopping, and over years, a push you cannot feel becomes a change in velocity nothing chemical could match. That is how you get to Mercury. Not with power, with patience, applied for the better part of a decade. The falling has not been comfortable. In April 2024, engineers found something wrong. Unexpected electrical currents running between the transfer module's solar array and the unit that draws power from it and distributes it to the rest of the spacecraft. The effect was that the ion engines could no longer produce the thrust the plan required. Months of investigation followed, and the conclusion was that the original arrival, December 2025, was no longer achievable. So they rebuilt the route. The flight dynamics team designed a new trajectory, including bringing one of the Mercury passes about 35 kilometers closer to the surface than planned, so that the planet's gravity would do more of the work the engines could no longer do. 35 kilometers. On a spacecraft that had already flown billions of kilometers, on a pass at a planet, they moved the aim point by a distance you could drive in half an hour, and it was enough to save the mission. The cost of that repair was 11 months. Not 11 months of work, 11 months of arrival. The science, the data, the pictures, the entire reason for the enterprise, all of it slid almost a year further into the future because of some unexpected current in a power supply. And the whole time, it has been getting hotter. This is the part of the Mercury journey that nobody puts on the diagram either. Inward is not just expensive. Inward is bright. At Mercury's distance from the Sun, sunlight arrives roughly 10 times more intensely than it does here. Not 10% more. 10 times. Everything you know about how sunlight behaves, how long you can stand in it, how quickly a dark object warms up, how hot a car interior gets on an August afternoon, you would have to multiply. Bepi Colombo has been descending into that all the way. Its orbiter carries a dedicated sunshield and a radiator system built for an environment where surrounding surfaces reach something like 350 degrees Celsius. The planet underneath is worse still. Daylight temperatures around 430 degrees. Night-side temperatures around minus 180. A swing of more than 600 degrees on one small airless rock every Mercury day. Picture the sun from there. Not the sun you see on a summer afternoon, a manageable disk you instinctively avoid looking at. From Mercury, it is a furnace filling a third of the sky, and there is no air to soften it, and no cloud to interrupt it, and no night that lasts less than weeks. It is not a light source. It is the dominant physical fact of the place. Hold on to that image of the furnace filling the window. I am going to give it back to you much later tonight, and it is going to look completely different. Mercury has broken the machines we sent before, too, in gentler ways. Mariner 10 reached the neighborhood in 1974 using a Venus flyby, but it could never stop. It made 3 passes and then drifted away, and we saw only the side of the planet that happened to be lit each time. Almost half of Mercury remained completely unmapped for the next 3 decades. Messenger, the first spacecraft ever to orbit it, launched in 2004, spent 6.5 years and 6 gravity assists getting into position, and finally settled into orbit in 2011. 2 orbiters. In 70 years of spaceflight. At the planet that is, on average, our closest. So the first payment is now on the table, and it is energy. The nearest world charges the most, because getting closer to the sun means giving up the speed that keeps you away from it, and nothing in physics gives that away for free. But energy is an odd thing to call a price, because you cannot feel energy. It is a line in an engineering document. If that were all this video had to offer, it would not deserve the word in its title. So let us go to the friendliest planet. Next, the cheapest ticket in the solar system. The one place a spacecraft can reach in a matter of weeks and see what happens when it gets there. In the autumn of 1962, a spacecraft weighing about as much as a large motorcycle spent 110 days crossing the space between Earth and Venus and then flew past it. It was called Mariner 2. It had no camera. It carried a microwave radiometer, an infrared radiometer, a magnetometer, and a few particle detectors. And it made the first successful visit to another planet in the history of life on Earth. 110 days. Less than 4 months. That is a single academic term. That is roughly the length of a pregnancy's second and third trimesters, or the time between planting something in spring and eating it in summer. And it happened 7 years before anyone walked on the moon. I find that ordering genuinely startling, and I think it is worth pausing on before we go any further, because it is a small crack in the picture people carry. We tend to imagine space exploration as a ladder we have climbed, one careful rung at a time. First the moon, then the planets, each step harder than the last. It did not happen that way. We flew past another planet before we could set anything down gently on our own satellite. Reaching another world turned out to be easier than stopping at one. Venus is the reason. Venus is the cheapest planetary destination in the entire solar system. The physics of that is straightforward once you have the Mercury lesson. Venus is inward from us, so getting there still means shedding some of that 30 kilometers per second, but only a little, because Venus is not far inward. Its orbit sits about 72% of the way out from the Sun compared to ours. You do not have to give up much of your sideways sprint to fall that far, and the planet is massive enough, almost exactly Earth's size, a shade over 80% of Earth's mass, to catch you comfortably when you arrive. By the measure that actually governs interplanetary travel, which is not distance but the total change in velocity required, Venus is the lowest number on the board. Lower than Mars. Lower than anything. The flight times reflect it. Mariner 2, 110 days. Pioneer Venus. In 1978, about 198 days. Venus Express, launched in 2005, 153 days. These are among the shortest crossings between worlds that anyone has ever flown, and they were flown with the technology of half a century ago. So Venus is easy. Venus is close. Venus is cheap. Venus is quick. Venus is the one planet where the diagram on the classroom wall is almost not lying to you. And Venus is where everything I have been telling you turns over. Because the arrival is the worst in the solar system. The surface of Venus sits at around 465 degrees Celsius. That is not a summer afternoon on a hot planet. That is hotter than a domestic oven at its maximum setting, hotter than the melting point of lead, hot enough that the ground itself glows faintly in the infrared. It is hotter than Mercury, which is twice as close to the Sun, because a thick blanket of carbon dioxide holds the heat in and will not let it leave. The pressure is about 92 times Earth's. To feel what that means, do not think about air. Think about water. 92 atmospheres is roughly the pressure you would experience 900 meters beneath the ocean's surface, far below where any diver can go, well into the depths where you would need a submersible with a hull thick enough to be its own kind of armor. That is the pressure at the bottom of the Venusian air and it is pressing on everything, everywhere, all the time. And the clouds are sulfuric acid. Every one of those three things by itself would be a serious engineering problem. Together, they produce the shortest deadline in exploration. The Soviet Venera landers are the most thermally aggressive machines human beings have ever built. They were constructed like deep-sea submersibles, titanium pressure vessels, sealed and reinforced, and before launch, their interiors were refrigerated, chilled down as far as possible, so that the whole spacecraft could act as a heat sink for a little longer once it arrived. They were not designed to survive. They were designed to fail slowly, in an orderly way, transmitting the whole time. The record for surface survival on Venus is 127 minutes. That is the record. 2 hours and 7 minutes. The best any nation has ever managed. Everything else lasted less. A machine crosses the space between planets in 110 days, descends through the acid, touches the ground, sends back photographs of a flat orange plain scattered with broken rock, and then the heat gets inside it, and the pressure finds a seal, and it stops. There is a small engineering absurdity buried in that, and I love it, so I am going to give it to you. Every spacecraft entering an atmosphere needs a heat shield, because the friction of arrival is violent and brief. On Earth, on Mars, on Titan, the shield does its job for a few minutes and is then dead weight, and the vehicle throws it away. On Venus, the entry is survivable and the ground is not. The hottest part of arriving at Venus is not the arrival. It is standing still afterwards. The shield protects the lander from a few minutes of entry heating, and then the lander sits down into an environment that is, in its own patient way, hotter than most of what the shield was built for, and this time there is nothing to fall through and no other side to come out on. The heat just stays, and time itself behaves strangely there. Venus turns once every 243 Earth days, which is longer than its year of 225. It also turns backwards. Put those two together, and a single day on Venus sunrise to sunrise lasts about 117 Earth days, with the sun rising in the west. A lander that survived the full record of 2 hours and 7 minutes experienced roughly 1/400th of one Venusian afternoon. So here is the inversion, and it is the second one tonight. The easiest place to reach is the hardest place to be. The cheap ticket does not buy you a good destination. It buys you the shortest possible visit. But Venus has a second job in this story, and it is the one I actually want to leave you with because it says something about how the whole solar system works. Venus is the brake pedal. Remember, the problem from Mercury inward means slowing down. Slowing down costs fuel, and fuel is the thing you cannot have enough of. Well, there is another way to slow down, and it does not cost anything at all. You fly past Venus. You come in on one side, let its gravity swing you around, and leave on a trajectory with less orbital energy than you had before. The planet takes it from you. You give up speed, and you pay nothing. Almost everything that goes inward uses this. Bepi Colombo used Venus twice on its way down to Mercury. And the most extreme example is Parker Solar Probe, the mission built to fly closer to the Sun than anything ever has, which used 7 separate passes at Venus over roughly 7 years, working its way down step by step, borrowing a little more room to fall on every single approach. 7 visits to the deadliest surface in the solar system by a spacecraft that had no interest whatsoever in Venus, purely to lose speed. There is something almost gentle about that arrangement once you see it. The planet that destroys everything that touches it is also the planet that most inward-bound missions could not function without. It is not an obstacle in the path. It is part of the machinery of the path. We could not reach the Sun without it. 2 payments collected now. Mercury took energy. Venus took the arrival it gave us, a cheap crossing, and charged us at the far end instead, in minutes of survival. Both of those are still prices paid by machines, though. Metal and budgets. Nothing so far has cost anybody anything they could feel. That changes at the next world out, and it changes in a way almost nobody expects. Because the frightening thing about Mars is not the distance, and it is not the landing, and it is not the dust, or the cold, or the thin air. It is the calendar. Somewhere in a building in California, there is a calendar with dates circled on it that nobody can move. They are not deadlines in the ordinary sense. A deadline is a decision somebody made, and decisions can be renegotiated. These dates were not decided by anyone. They come out of the way 2 planets happen to orbit, and they arrive when they arrive. And if you are not ready on the day, the answer is not, "We will push it back a week." The answer is, "We will see you in 2 years and 2 months." This is the part of Mars that never makes it into the conversation, and I think it is genuinely the most unsettling thing about the place. More than the cold, more than the dust, more than the thin air. Mars does not have a distance problem. Mars has a scheduling problem, and the schedule is not ours. Let me give you the numbers everybody half knows first, so we can put them behind us. The closest Mars has come to Earth in modern times was in 2003 at 55.76 million kilometers, the nearest approach in something like 60,000 years. The farthest the 2 planets get is around 400 million kilometers. The average separation is roughly 225 million, which is a light travel time of about 12.5 minutes each way. Actual robotic crossings run 7 to 9 months. Mars Reconnaissance Orbiter took about 7, Curiosity took about 8.5. Fine. Those are the numbers on the poster. Now here is the structure around them, which is where the fear lives. Earth goes around the Sun in a year. Mars takes about 1 year and 10.5 months. Because we are moving faster on the inside track, we lap Mars regularly, and the interval between one favorable alignment and the next, the interval astronomers call the synodic period, is about 780 days. Roughly 26 months. That is the door. It opens for a few weeks. Then it closes for 2 years and 2 months, and there is nothing anybody can do about it. Outside that window, a Mars mission is not merely more expensive. It moves into the region where the required fuel stops being a budget question and starts being a physics question, where the amount of propellant needed exceeds what any existing launch vehicle can put into space. The window is not a preference. It is the difference between possible and impossible. You can feel the shape of this in the historical record if you look at launch dates. Missions to Mars cluster. 1996 had a rush of them. 2003 had a rush of them. 2020 had a rush of them, 3 separate nations, launching within a couple of weeks of one another, not because of any competition, but because the door was open and the next one was 2 years away. Every space agency on Earth is on the same timetable, set by the geometry of 2 orbits, and none of them chose it. So a departure to Mars is not a decision in the way we normally mean the word. It is an appointment. And that appointment structure does something extraordinary to what a crewed mission actually looks like. Something that I would guess most people listening have never heard, and which changes the whole shape of the enterprise. Ask almost anyone how long a trip to Mars takes, and they will say something like 8 months. That number is not wrong. It is simply the smallest part of the answer. The standard architecture, the low-energy one, the one every serious mission study starts from, called a conjunction class mission, works like this. You leave when the door is open. You cross in roughly 180 to 210 days. And then you land on Mars. And you stay. You stay for 500 days. Not because there is 500 days of work to do, because the Earth and Mars have to come back around into the right positions for the return leg to be affordable, and that takes 500 days or more. You cannot leave early. There is no cheaper window in between. You wait on the surface, watching a sky the color of weak tea for a year and 4 months, until the planets are aligned to let you go. Then you cross back. Another 180 to 210 days. Total mission duration, roughly 900 days. 2.5 years. And the majority of it, over half, is spent standing still. Think for a moment about what 500 days actually requires in the most ordinary domestic terms. Every meal for that period has to be already there when the crew arrives, or grown, or manufactured. Every filter, every seal, every spare pump, every dose of every medicine anyone might need has to have been chosen and packed years earlier by someone guessing at what would go wrong. There is no delivery. There is no shop. There is not even the possibility of an unplanned resupply, because a resupply ship would face exactly the same closed door and the same 2-year wait. The habitat is not a base with a supply line. It is a sealed room with a fixed inventory and a date on it. And getting down to that room is its own quiet problem, because Mars has the worst atmosphere in the solar system for landing. It is about 1% of the pressure at sea level here, thick enough that a vehicle arriving at interplanetary speed will burn without a heat shield, and far too thin for that heat shield alone to slow it to a survivable speed. You need the shield and the parachutes and the rockets, all three in sequence in about 7 minutes with no possibility of a second attempt. Historically, roughly half of all missions ever sent to Mars have failed, which is the worst record of any target we have tried for. There is an alternative, and it is worth knowing about because of what it reveals. It is called an opposition class mission, and it cuts the total time down to something under 760 days. Sounds better. Here is what it costs. The surface stay drops from 500 days to something like 30 to 50. You travel for the better part of 2 years to spend a month there. And it requires substantially more energy, and typically a swing inward past Venus on one leg, which means adding extra solar heating and extra radiation exposure to the bill. So the choice on the table is not long trip or short trip. The choice is be away for 2.5 years and actually do something, or be away for 2 years and barely touch the place. You can have a shorter mission or a useful one. The geometry will not sell you both. And underneath all of that sits the fact that I think is the true weight of this part. There is no abort. Once the departure burn is finished, once that engine shuts down and the vehicle is coasting, the crew is on an orbit around the Sun. Not a route. An orbit. They are a small object following the same laws as every asteroid, and the only thing that could change their path is an engine burn. And the propellant for a burn large enough to turn around and come home was never loaded, because loading it would have made the vehicle too heavy to leave in the first place. Mission designers do use something called a free return trajectory, and it is a genuinely elegant idea. You aim on a path that, if you do nothing at all, will eventually swing back and encounter Earth again. Some Mars mission designs include one, but a free return from Mars is not a rescue. It is a coast of roughly 2 years, with no landing, no resupply, and no change of plan, ending at Earth. It is not an escape hatch. It is a very long promise. I want to state this plainly, because it is the thing an audience feels rather than calculates. On Earth, almost every commitment a person makes can be revised. You can turn the car around. You can come home early. You can walk out of the room. It might be expensive. It might be embarrassing. It might cost you something real. But the option exists, and the quiet knowledge that it exists is underneath almost everything we do. On a Mars mission, that option is not expensive. It is absent. It cannot be bought at any price by any government for any reason, because the propellant to buy it does not exist on the vehicle, and never did. Whatever happens on day 100, a fault, an illness, a death in a family back home, a change of mind, a loss of nerve, is handled with what is on board, or it is not handled. I do not think that is a horror. I think it is something stranger and quieter than horror. It is the removal of an option so fundamental that most people have never once consciously noticed they rely on it. And there is a small, almost absurd detail that makes the isolation physical rather than philosophical. Roughly every 2 years, Mars passes behind the Sun as seen from Earth. It is called solar conjunction, and while it lasts, hot ionized gas streaming off the Sun's outer atmosphere sits directly in the path of any radio signal between the two planets and can scramble it. So NASA stops talking. There is a formal 2-week moratorium on sending commands to the Mars fleet, and the rovers and orbiters are loaded with instructions in advance and simply left to get on with it, alone, until the geometry clears. For robots, that is an inconvenience noted in a mission log. For a crew, it would be 2 weeks of silence from the entire human species, scheduled in advance, happening twice inside a single mission, with everyone aware of the date well beforehand. So the third payment is on the table, and it is the first one that costs a person something rather than a budget. Mercury took energy. Venus took the arrival. Mars takes your ability to change your mind. And that is still only the structure of the thing. That is the shape of the journey, not the substance of it. Because the whole time the crew are sitting inside that unchangeable schedule, something else is happening to them, continuously, at a steady, measured rate, every hour of every one of those 900 days. And unlike everything so far, it does not stop when they get home. There is a small grey box, about the size of a toaster, that spent 8.5 months in 2011 and 2012 flying to Mars inside a spacecraft, quietly counting. It was called the Radiation Assessment Detector, and it was bolted to the deck of the Curiosity rover, which was itself folded up inside an aeroshell for the crossing. And that arrangement, a detector buried inside a spacecraft, behind ordinary spacecraft structure, is the closest thing anyone has ever built to a stand-in for a human being on the way to Mars. That is what makes it precious. Before it flew, everything we thought we knew about the radiation environment of a Mars cruise came from models, from calculations about what ought to be out there, and estimates of how much of it would get through a hull. This box did not calculate anything. It sat where a person would sit, behind roughly the shielding a person would have, and it measured what actually arrived. The results were published by Kari Zeitlin and his colleagues in the journal Science in 2013, and the central number is this. During the cruise, the average dose equivalent was about 1.8 millisieverts per day. I need to make that number mean something, because on its own, it is just a unit nobody uses in ordinary life. A chest X-ray delivers somewhere around 1/10 of a millisievert. A detailed scan of the abdomen, the kind where you lie in a tube and are told to hold your breath, is around 10. And the average person going about their life on the surface of this planet, from all natural sources put together, from the rocks and the air and the food and the sky, receives roughly 3 millisieverts in a year. 3 in a year. The cruise to Mars delivers 1.8 in a day. Every day. More than half a year's worth of natural exposure, arriving each day for 200 days, without a break, and then the same again on the way home. Put together, the transit phases alone, just the 2 crossings, not counting a single hour spent on the surface, come to roughly 0.66 sieverts. A full conjunction-class mission, the 900-day version we walked through in the last part, comes out somewhere on the order of 1 sievert. The convention used in radiation protection is that a sievert corresponds to something like a 5% increase in the lifetime risk of a fatal cancer. And NASA has historically worked to a career limit for its astronauts in the region of 0.6 sieverts, with the European Space Agency's figure closer to 1. So look at what that means. Not the risk, the bookkeeping. A single trip to Mars spends an astronaut's entire career radiation allowance and then keeps spending past it. Not their allowance for that mission. Their allowance for their whole working life, all of it, on one journey. And here is the part that I think genuinely earns the word in tonight's title, because it is the point where the intuitive solution turns around and fails. The obvious answer is shielding. Put more metal around the crew. This is what everybody assumes, and it is what I assumed for a long time. And it does not work the way you expect. The radiation out there comes in 2 kinds, and the chronic one is galactic cosmic rays atomic nuclei that were accelerated somewhere in the galaxy, often by supernovae, long ago and far away, and have been traveling ever since at a substantial fraction of the speed of light. Most of them are hydrogen nuclei. Some are helium. And a small but important fraction are heavy things, carbon, oxygen, silicon, iron, moving at speeds that make them, individually, extraordinarily energetic. When one of those heavy nuclei strikes a sheet of aluminium, it does not stop. It has far too much energy for that. What it does instead is shatter, and the fragments carry on, and each one of them is itself an ionizing particle. One fast, heavy nucleus goes in. A spray of lighter particles comes out the other side, spreading as it goes. Which means that a thin metal shield can increase the biological dose behind it. Not reduce it. Increase it by taking one problem and turning it into a shower of smaller ones distributed over a wider area. The material that actually helps is the opposite of what intuition suggests. You want light atoms, not heavy ones, hydrogen-rich substances that break the incoming particles down without producing so much secondary debris. Water works. Polyethylene works. Human waste and food stores, awkwardly enough, work quite well. And you need a great deal of it. Not a lining. Thicknesses measured in tens of centimeters, and for real protection, meters. Meters of water is mass. And mass is the one thing in spaceflight you cannot simply decide to have, because every kilogram added to the vehicle has to be accelerated by fuel, and the fuel to accelerate it has to itself be accelerated, and the arithmetic climbs on itself until the answer stops being a design and starts being a fantasy. The shielding that would solve the problem is a shielding no rocket will lift. There is a subtlety hiding in the unit itself, And it is worth 30 seconds because it explains why this environment is not simply more of the X-ray you had at the dentist. An X-ray deposits its energy diffusely, spread thinly through a great many cells, and most of those cells repair themselves without any drama at all. A heavy nucleus does not do that. It carves a narrow track, and everything along the line of that track receives an enormous local dose, while the tissue a millimeter away receives nothing. Same total energy. Completely different pattern. That is why the sievert exists as a separate unit from the raw energy measurement. It is a weighted number, adjusted for the fact that some kinds of radiation are simply harder for a body to repair than others. 3. And the heavy nuclei of galactic cosmic rays sit at the difficult end of that scale. It is the difference between being rained on and being stitched. There is one more piece of unwelcome arithmetic. The sun helps in a way nobody expects. When solar activity is high, the sun's own outflow pushes back against the galactic particles arriving from outside the solar system and thins them out. So the chronic cosmic ray dose is actually lower during a busy sun and higher during a quiet one, which means that the safest time to fly for chronic exposure is the most dangerous time to fly for storms, and the safest time to fly for storms is the worst time for chronic exposure. There is no month in the 11-year cycle that is good for both. That is the chronic exposure. Now the other kind. On the 4th of August 1972, a region on the surface of the Sun catalogued as McMath 11,976 produced 3 enormous flares within about 15 hours of each other, and threw out one of the largest storms of solar particles recorded in that era. Here is the timing. Apollo 16 had come home in April. Apollo 17 would not launch until December. The storm arrived in the gap. What would have happened to a crew caught in it is genuinely disputed. And I want to be honest with you about that, rather than give you a clean number that sounds authoritative. The estimates vary depending on who did the analysis and what assumptions they made about shielding and location. Figures in the region of 1 to 4 sieverts appear in the literature for an exposed crew. One analysis gives a skin dose of 600 rem and a dose to the blood-forming organs of around 130 rem for astronauts on the lunar surface in ordinary suits. Different sources will give you different answers, and anyone who tells you the exact figure with confidence is telling you more than the data supports. What is not disputed is the range those estimates cover. It runs from serious acute radiation sickness at the low end to fatal at the high end. And the only reason the question stayed academic is a 4-month gap in a launch schedule that nobody arranged on purpose. A storm of that class during a Mars cruise cannot be avoided. There is no planet to put between yourself and the sun. There is no magnetic field. The standard answer is a storm shelter, a small volume in the middle of the vehicle, packed around with water tanks and food and waste and anything else dense and hydrogen-rich, into which the crew climbs and stays for hours or days until it passes. It is a good solution to the acute problem. It does nothing whatsoever about the chronic one, because you cannot spend 200 days inside a cupboard. I want to slow down here for a moment, because I have given you a great many numbers, and numbers are not what this actually is. Lie still. It is 2 months into the crossing. The cabin lights are down. Whatever there is to do has been done, and you are floating loosely against a restraint, eyes closed, in the specific dark of a room with no windows lit. Somewhere outside, an iron nucleus that has been traveling since a star exploded long before the sun existed comes through the hull. It does not slow down. It comes through the wall of the cabin, and through the air, and through you, and as it crosses the back of your eye, or somewhere in the visual part of your brain, it leaves a mark on the machinery there. And you see it. A thin white flash, or a streak, or a small bright point behind closed eyelids in a dark room with nothing there to make light. It is gone before you can decide whether it happened. There is no sound. There is no sensation of impact, no heat, nothing that registers as being struck. Just the flash, and then the ordinary dark again. 4 minutes later, another one. The Apollo crews reported this. On the way to the moon, with their eyes shut, they saw flashes at rates of roughly 1 every 1 to 3 minutes. It has been reported on every long-duration mission since. It is the only radiation environment a human being can directly perceive. And what makes it strange is how gentle it seems. Not an alarm, not a pain, just a quiet, regular, silent arrival of visitors, going through you and continuing on their way. So that is the fourth payment, and it is the first one that is unambiguously charged to the person rather than to the mission. Mercury took energy. Venus took the arrival. Mars took the ability to change your mind. And the crossing itself takes cells at a measured rate every day, in a currency that does not get refunded at the far end. But there is something else happening in that cabin over those 200 days, and it has nothing to do with radiation at all. It began within hours of leaving Earth. It is completely silent, and it is happening to every part of the body at once. Within about 4 hours of arriving in freefall, an astronaut's face changes shape. It is one of the first things anyone notices in footage from a new arrival at the space station. The cheeks fill out. The eyes look slightly smaller. There is a puffiness across the forehead and around the nose that is not there in the pre-flight photographs. And it is not weight gain, and it is not swelling from injury. It is roughly 2 liters of fluid that had been sitting in the legs, held there by gravity for the person's entire life, arriving in the head and deciding to stay. That is the body's first response to leaving Earth, and it is a good introduction to the whole problem because the body is not being damaged. It is doing exactly what it evolved to do. It is adapting sensibly and efficiently to the environment it finds itself in. The trouble is only that the environment it finds itself in is one no ancestor ever experienced, and the adaptations it makes are all in the wrong direction. Start with bone. Bone is not a static scaffold. It is a living, continuously rebuilt tissue, and the rebuilding is driven by load. Every time you stand, walk, or carry something, the strain in your skeleton tells the cells that maintain it to keep it strong. Remove the load, and the message changes. The body, entirely reasonably, concludes that this expensive mineral is not being used, and begins to reclaim it. The measured rates in long-duration cruise run at roughly 1 to 1.5% of bone mineral density per month in the weight-bearing regions, the hips, the lower spine, the legs. A systematic review looking across many crews puts the lower limb figure at around 0.8% per month. For comparison, flight surgeons often point out that this is somewhere around 10 times the rate of bone loss seen in terrestrial osteoporosis after menopause. 10 times. Sustained, month after month. Over the 900 days of a conjunction-class Mars mission, even with countermeasures, the cumulative figure becomes serious. And crews do fight it. The exercise program aboard the space station takes about 2.5 hours of crew time every single day, resistance work against machines that simulate lifting, a treadmill with a harness that pulls the body down onto it, a cycle ergometer. It slows the loss substantially. It does not stop it. And recovery, once back on the ground, is slow and not always complete. Studies that have followed crews for a full year after landing have found vertebral bone density and the muscles alongside the spine still measurably different from their pre-flight state 12 months later on Earth, with gravity doing its work every hour of every day. Then there is the eye, which is the strangest part of this, and the part I did not expect when I first read about it. Remember the 2 liters of fluid that moved up into the head. It does not simply make the face puffy. It changes the pressure environment inside the skull, and it does so continuously, for months. And behind the eye, where the optic nerve enters the back of the eyeball, that change in pressure produces something visible. The condition has a name: spaceflight-associated neuroocular syndrome. Its signature finding is swelling of the optic nerve head, and it has been observed in up to roughly 70% of astronauts on long-duration missions. One study, using a strict measurement threshold, a 20-micron increase in the thickness of the retina immediately around the nerve, puts the prevalence around 64%. Alongside it come other changes. The back of the eyeball flattens slightly, which changes the eye's focal length. Folds appear in the layer of tissue behind the retina, and crew members become measurably more far-sighted while in orbit, to the point where the space station carries a supply of what are informally called space anticipation glasses, a range of reading strength lenses, so that an astronaut whose vision has shifted mid-mission can simply select a different pair. Some of it resolves after landing. Some of it has persisted for years. And nobody has a complete mechanism for it, and nobody has a countermeasure that reliably works. Underneath those 2 headline effects sits a longer list, all of it documented. Postural muscles atrophy, because nothing is holding the body upright anymore. The cardiovascular system deconditions, because the heart no longer has to pump uphill, so returning crews frequently cannot stand without their blood pressure collapsing. The immune system shifts in ways that are still being characterized, and latent viruses of the herpes family, the ones most adults carry quietly for life, reactivate in a significant fraction of crews. Sleep is disrupted, partly by the 16 sunrises a day in low orbit, and partly by simple noise and stress. And the carbon dioxide level in a sealed cabin runs several times higher than typical indoor air on Earth, with crew reports of headache and mental fog tracking the peaks. And then there is the part that no instrument measures directly, which is what it does to a person to be sealed in a small volume with the same 5 faces for 2.5 years, unable to leave, unable to be alone, and unable to be reached quickly by anybody who loves them. We have tested that piece separately, without any of the physics attached. Between 2010 and 2011, a crew of 6 men were sealed into a facility in Moscow for 520 days, running a complete simulated Mars mission outbound cruise, surface operations in a mock-up, return cruise with realistic communication delays, and no way out. It was called Mars 500, and it finished in November 2011. There was no radiation. There was no weightlessness. There was no actual risk to anyone's life, and every participant knew at every moment that a door existed and that walking out of it would cost them nothing but the study. Even so, most of the crew showed significant disruption to their sleep and their activity patterns over the course of the run. One of them shifted onto a 25-hour cycle and gradually drifted out of phase with everyone else, awake while the others slept, for weeks at a time. Another spent an increasing share of the mission simply inactive. The physical health of the group was fine throughout. It was the rhythm of being a person that came apart. The nearest thing to this on Earth outside a laboratory is an Antarctic research station in winter. Once the last aircraft leaves, the crew are genuinely unreachable for months, in the dark, with a fixed group and a fixed inventory, and there is a documented pattern of cognitive slowing, irritability, and low mood common enough that it has an informal name, winter over syndrome. Those stations are on this planet. They have breathable air outside the door and a horizon to look at. Set against all that, the record we have is Scott Kelly's 340 consecutive days aboard the space station, flown between 2015 and 2016, with his identical twin brother on the ground as a control, the most detailed physiological record of long-duration spaceflight ever assembled. 340 days sounds like most of the way to a Mars mission. It is roughly a third. And it was flown 400 kilometers above the ground, inside the Earth's magnetic field, which deflects most of the charged particles we spent the last part discussing. It was flown with cargo ships arriving regularly, bringing food, spare parts, and letters. And it was flown with a return vehicle docked to the station the entire time, capable of bringing the crew home within hours if anything went seriously wrong. None of those three conditions exists past Earth orbit. Not the magnetic field, not the resupply, not the ride home. Let me stop here for a moment and put down what we have, because we are about halfway through tonight and we have collected quite a lot. 5 payments so far. Mercury charged energy the price of losing the speed you were born with. Venus charged the arrival, giving us the cheapest crossing in the solar system and taking it back at the far end, in a survival record of 127 minutes. Mars charged the abort the removal of the option to change your mind, enforced by a door that opens every 26 months. The crossing itself charges dose at 1.8 millisieverts a day, in a currency the body does not refund. And the body charges itself, quietly, from the first 4 hours. Now look at what those 5 have in common, because I think it is the thing this whole video is circling. Every single one of them is metered by duration. The energy cost is a function of the trajectory, and the cheapest trajectories are the slowest ones. The abort exists or does not exist, depending on how long the alignment takes to come round. The radiation dose is not a fixed amount you receive on arrival. It is a rate, 1.8 per day, and the total is simply the rate multiplied by the number of days. The bone loss is 1% a month. The number of months is the whole story. Even the survival time on the surface of Venus is a clock. Nothing out there charges by the kilometer. Everything charges by the hour, which means the price of the ticket, itemized, comes to the same line 5 times over, written 5 different ways. Hold that, because we are about to leave the inner solar system, and everything from here outward is measured in years rather than months. Ahead of us is a band of rubble that everyone has been told is dangerous and is not. And beyond it, something that genuinely is a hazard you cannot see, cannot shield against with any reasonable mass, and which does not care in the slightest whether the thing crossing it is alive. In July of 1972, a spacecraft about the size of a small car, spinning slowly to keep itself steady, crossed a line that nobody was sure could be crossed. Pioneer 10 was the first object ever sent into the asteroid belt, and at the time the engineers who built it genuinely did not know what would happen to it. The belt was a region of the solar system known to contain an enormous quantity of rock, and the honest position was that nobody could say how densely that rock was distributed. Estimates of the risk of a mission-ending impact ranged from negligible to serious enough that the crossing was listed as one of the mission's major hazards, on a par with the launch. It took about 7 months to get through. Nothing happened. That is the entire story, and it is one of the most useful results in the history of planetary exploration, because it deleted a fear that a great many people are still carrying. the asteroid belt is not a hazard. The popular image, a spacecraft weaving frantically between tumbling boulders, alarms sounding, is one of the most successful pieces of misinformation the 20th century produced. The truth is dull and enormous. The belt contains a great deal of material, a few million objects larger than a kilometer, and vastly more that are smaller. But it is spread through a volume so large that the typical separation between two objects big enough to matter is on the order of hundreds of thousands to millions of kilometers. If you were standing on one asteroid, in almost every case, you would not be able to see another one as anything more than a point of light indistinguishable from a star. Spacecraft do not maneuver to avoid asteroids. They cannot even find one to look at without aiming for it deliberately. Every mission that has photographed an asteroid close up did so because someone spent propellant and planning to arrange the meeting. The belt is not something you thread. It is something you fall through, for months, seeing nothing. If you gathered every asteroid in it together into one body, the result would be smaller than our own moon, a few % of the moon's mass, scattered across a ring hundreds of millions of kilometers wide. The famous danger is a small amount of gravel in a very large room. So we get a small reprieve in this part. One of the things you were told to be afraid of turns out not to be there. What is there, instead, is the crossing time, and the crossing time is where the shape from the first part comes back. Pioneer 10 reached Jupiter in about 640 days. Voyager 1, launched 5 years later on a faster trajectory, made the same crossing in roughly 546. Those are flybys, though arriving at enormous speed, taking pictures for a few days and continuing outward forever, because stopping was never part of the plan. The moment you want to stop, the numbers change completely. Galileo, which had to arrive slowly enough for Jupiter to catch it, launched in 1989 and did not enter orbit until about 6 years later, having borrowed speed from Venus once and from Earth twice on the way. Juno launched in 2011 and arrived in 2016. Europa Clipper left in October 2024 and arrives on the 11th of April 2030. 5.5 years for a gap of 600 million kilometers along a path 2.9 billion kilometers long. That ratio again. It has followed us out from the first part, and it never improves. You do not travel to a planet. You fall past where it is going to be, and out here, the falling takes years. And then the light starts to go. This is the point in the outward journey where the physics changes character, and it changes because of something so simple that it barely feels like a fact. Light spreads out. A given amount of sunlight leaving the sun has to cover a sphere, and the sphere gets bigger as you go, and the amount of light landing on any square meter of that sphere falls off with the square of the distance. Double the distance, and you have a quarter of the light. That is the whole rule. At Jupiter, roughly 5 times further from the Sun than we are, sunlight arrives at about 1/27th of the intensity it has here. I want to make that concrete rather than mathematical. Think about how much light there is outdoors on a clear day. Now think about how much light there is in a room lit by a single lamp in the corner. That is roughly the scale of the change. It is not darkness. Jupiter is well lit, in the sense that you could read out there. But every device that lives on sunlight has just had 26/27ths of its supply removed. For a spacecraft, this is not an aesthetic matter. It is the difference between having a power system and not having one. Juno is the demonstration of how far solar power can be pushed, and it is a slightly absurd machine because of it. It carries 3 solar arrays, each about 9 meters long, arranged in a three-armed pinwheel, a spacecraft that is mostly wings. Between them, they hold something like 18,700 individual solar cells. If you brought Juno back to Earth's distance and pointed it at the Sun, those panels would produce something on the order of 14 kilowatts, which is enough to run a small building. At Jupiter, they produce a few hundred watts. A few hundred watts is roughly what a couple of desktop computers draw. That is the entire electrical budget of a spacecraft the size of a basketball court, orbiting the largest planet in the solar system, running its instruments, its heaters, its radio, and its computers. Juno works only because it is exceptionally frugal, because its orbit is designed so that it is almost never in shadow, and because it turns slowly to keep those panels facing the light at all times. Europa Clipper, the spacecraft we started tonight with, currently on its way back to Earth for a flyby in December, takes the same approach further. Its solar array span is roughly 30 meters, tip to tip, which makes it the largest spacecraft NASA has ever built for a planetary mission. Almost all of that size exists for one reason: to gather enough of a light that has become 27 times too thin. There is a thermal side to this too, and it is easy to overlook because we spend so much time talking about power. Sunlight is not only the electricity supply, it is also the heating. In the inner solar system, the problem is getting rid of heat. Bepi Colombo, falling toward Mercury, is fighting to stay cool. Past Mars, the problem inverts entirely. Every spacecraft out here carries heaters, and those heaters consume a substantial fraction of the same electrical budget that is already 27 times thinner than it would be at home. The instruments have to be kept warm enough to work. The propellant has to be kept warm enough not to freeze in the lines. So the further out you go, the more power you need for warmth, and the less power you have two curves moving in opposite directions, meeting somewhere out past the orbit of Jupiter, and everything beyond the meeting point requires a different answer. And Jupiter is where solar power stops. Past this point, you would need panels of a size nobody can fold into a rocket fairing, and the answer has to be something else entirely. So the outer solar system has begun to charge its own price, and it is charging it in light, which becomes power, which becomes what a spacecraft is allowed to do when it arrives. But that is not the reason Jupiter is dangerous. The reason Jupiter is dangerous is a thing you cannot see, cannot detect with any instrument on your own body, cannot shield against without enormous mass, and which does not care in the slightest whether the object crossing it is alive or not. It has already ended one spacecraft's mission by slow attrition. It is the reason a mission built specifically to study a moon is not allowed to orbit that moon. And the engineering answer to it is the single most direct thing anyone has ever built for a spacecraft: a metal box with walls a centimeter thick, weighing as much as 3 people. In a clean room in Colorado, in the summer of 2010, a crane lowered a titanium box onto the deck of a spacecraft. The box had 6 sides. Each wall was about a square meter in area, roughly a small tabletop, and about a centimeter thick. Solid titanium, at that thickness, over that area, 6 times over. Sources differ a little on the exact number, but the whole assembly weighed somewhere in the region of 170 to 200 kilograms. Call it the weight of 3 adults, in metal, in a cube. Technicians in white suits and gloves stood around it, guiding it down with their hands as the crane took its time. It came to rest on the hexagonal deck of the spacecraft that would carry it, and was bolted into place. Inside it went the flight computer, the part of Juno that thinks, the part that decides what to do, holds the instructions, runs the instruments, and manages every second of the mission, sealed into a vault because the engineers who built it had concluded that there was no other way to send a computer to Jupiter and expect it to still be a computer when it got there. Picture the room while it happens, because it is a very ordinary scene and it is doing a very strange thing. The light is flat and even, the way it always is in a clean room, with no shadows anywhere. Everyone is in white coveralls, hoods, masks, 2 pairs of gloves. Nobody is hurrying. The crane moves at the speed cranes move, when what is hanging from them is irreplaceable, which is to say, barely at all, in increments, with someone calling out the clearance. 2 technicians walk the box down with their palms flat against its sides, not really supporting the weight, just keeping it true. You can hear the air handling. You can hear the crane motor. That is about all there is to hear. And what is happening in that quiet, unremarkable industrial moment is that a group of people are building a shelter for a thing that cannot ask for one. They have worked out, on paper, what a place 600 million kilometers away will do to a piece of silicon, and they have concluded that the only workable answer is a wall. And then they have machined the wall and lifted it, and are now setting it gently down over the part of the spacecraft that thinks. The box touches down. Someone begins the bolts. I find that genuinely striking, and I want to leave it with you before we get to why. Not a shield. Not a coating. A room. A small titanium room built around a machine, so that the machine could survive being somewhere. Here is what it is a room against. Jupiter has a magnetic field, and it is the largest structure in the solar system after the domain of the Sun itself. If you could see it in the sky from here, it would appear several times wider than the full moon, despite being 600 million kilometers away. It is generated deep inside the planet, in a layer of hydrogen compressed so hard that it behaves like a liquid metal, and it is roughly 20,000 times stronger than the Earth's. A magnetic field that size does something specific to charged particles. It traps them. Any electron or ion that wanders in finds itself following the field lines, bouncing back and forth between the poles, accelerated a little more on each pass. Over time, this builds up regions of intensely energetic particles held in place around the planet, radiation belts. The same phenomenon Earth has in the Van Allen belts, except scaled up to something no laboratory on this planet can reproduce. And Jupiter keeps them fed. The moon Io, tugged and squeezed by Jupiter's gravity, is the most volcanically active body in the solar system, and it throws off something on the order of a ton of sulfur and oxygen every second. That material gets stripped of its electrons, caught by the field, and accelerated into the belts. The moon is quietly supplying the ammunition. What that does to a spacecraft is not what most people picture. Nothing is struck. Nothing is punctured. The damage is at the scale of individual atoms. High-energy particles pass through the silicon of a microchip and knock atoms out of position in the crystal lattice, permanently, one at a time. Enough of those displacements, and a transistor stops behaving like a transistor. Memory develops errors. Sensors drift. Nothing dramatic happens on any given day, and then one day, the machine is no longer reliable. You can see the consequence of all that trapped energy without any instrument at all, if you point the right telescope at the right wavelength. Jupiter's poles carry permanent aurorae, the same phenomenon as the northern lights here, produced by charged particles funneling down the field lines into the atmosphere, except that Jupiter's are hundreds of times more powerful than anything Earth has ever produced. They never switch off, and they are larger across than our entire planet. On Earth, an aurora is a gift from a solar storm, arriving occasionally, lasting hours. At Jupiter, it is a fixed feature, burning continuously at both poles, powered not by the sun, but by the planet's own rotation, dragging its enormous field around once every 10 hours. The figures quoted for what an unprotected surface on Juno would accumulate over the mission run into the tens of megarads. The vault reduces that by a factor of several hundred. Everything Juno has done at Jupiter, it has done because of that box. Galileo, which had no such vault, shows what the alternative looks like. Through the 1990s, as it orbited Jupiter, it accumulated damage and began to develop problems, trouble with its tape recorder, repeated instances of the spacecraft putting itself into a protective, safe mode, sensors behaving oddly. It kept working, and the team kept nursing it, but the mission's later years were a managed decline. In 2003, they flew it deliberately into Jupiter's atmosphere and destroyed it. That last decision is worth pausing on, because it explains something about how seriously the outer moons are taken. Galileo was not destroyed because it was finished. It was destroyed because it was dying, and a dying spacecraft eventually stops responding to commands. And a spacecraft that no longer responds to commands is an uncontrolled object in a system that contains Europa, a moon with a liquid water ocean beneath its ice. The risk of eventually crashing a machine covered in Earth bacteria into that ocean was judged unacceptable. So they steered it into the planet while they still could. Cassini was destroyed at Saturn for the same reason, 14 years later. Now, Europa itself. This is the number that lands hardest, and it is the reason the current mission is designed the way it is. The radiation environment at Europa's surface is commonly quoted at around 5.5 sieverts per day. Go back to the last part but one. The entire round trip to Mars, both crossings together, was 0.66 sieverts. The whole career limit for an astronaut, historically, has been in the region of 0.6. 5.5 sieverts per day, standing on the ice. For an unshielded human being, that is a lethal exposure in something on the order of 10 to 20 minutes. Not sickness. Not an elevated risk to be managed over decades. A lethal dose in the time it takes to boil a kettle and drink the tea. And this is why Europa Clipper is not going to orbit Europa. The mission exists to study one moon, and it will never spend more than a few hours at a time near it. Instead, it orbits Jupiter on a wide, looping, elliptical path that spends most of its time far out where the belts are thin and dips inward for close passes, roughly 49 of them planned grabbing data on the way through and getting out again. The whole architecture of the flagship mission to Europa is designed around the fact that Europa is a place a spacecraft can only visit briefly 49 times over 4 years and survive. So the sixth payment is on the table, and it is the strangest one so far, because it is charged to the machine rather than to the traveler. Jupiter does not take fuel, or time, or bone. It takes the working lifetime of electronics, quietly, at the atomic scale, in a way that nothing on board can feel happening and nothing can repair. Which raises the question that has been sitting underneath this whole outward journey without being asked. If something goes wrong out here, if a sensor drifts, if a computer starts making errors, if a valve sticks or a thruster misfires, who fixes it? The honest answer to that turns out to be one of the quietest and coldest facts in this entire video, and it has nothing to do with skill, or funding, or courage. It is a property of the universe, and it has already been sitting in every number I have given you tonight without either of us naming it. Hold up your hand in front of your face, close enough to see the lines on your palm. The light bouncing off that hand reached your eye about 1/1000th of a second ago. For every ordinary purpose, that is 0. When you look at something in the room with you, you are seeing it now. When you speak to someone across the table, they hear you as you say it. The whole texture of being with another person, the interruptions, the overlapping, the small adjustments made halfway through a sentence because of the look on their face, depends on a delay so short that no one has ever noticed it exists. That is a local arrangement. It holds in this room. It does not hold anywhere else, and the further out you go, the more comprehensively it stops holding, until eventually it takes away something people do not realize they have. Let me walk the ladder with you, one rung at a time. The moon is about 1 1/3 light seconds away. You can hear this in the Apollo recordings. If you listen for it, a small hesitation before every reply, about 2.5 seconds for the round trip, which the crews and the controllers simply learn to talk around. It is a slightly awkward phone call. It is still a phone call. Mars runs from roughly 4 light minutes at its closest to about 22 at its furthest. Call it 12.5 on average. That is the end of conversation. A question asked and answered takes between 8 and 44 minutes to complete. You cannot interrupt. You cannot check whether you have been understood. Everything becomes correspondence. You compose a message, you send it, you go and do something else, and eventually a reply arrives, written by someone responding to a version of the situation that has already moved on. Jupiter is roughly 33 to 53 light minutes. Saturn is about 68 to 84. Uranus is around 2.5 hours. Neptune is about 4. And Pluto, at the moment New Horizons flew past it in July 2015, was around 4.5 light hours away, which made a single exchange with the spacecraft, a question sent and an answer received, take roughly 9 hours. Now, these are usually presented as a communications inconvenience, a bandwidth issue, something engineers work around with clever scheduling. They are not. They are a hard limit on what the word help can mean. Think about what help actually consists of here on the ground. Something goes wrong. You notice. You tell someone. They understand the situation, they think about it, they tell you what to do, and crucially, they are watching while you do it. So if the situation changes, they change their advice. Help is not information. Help is a loop, and the loop has to close faster than the problem develops. At 1 1/3 seconds, the loop closes. At 12 minutes, the loop closes far too slowly for anything urgent. But you can still get advice on anything that unfolds over days. At 33 minutes, an entire emergency can begin, develop, and finish before the first message even arrives. So somewhere out past Mars, help stops being far away and starts being a category that does not apply. That is worth sitting with, quietly, because it is the coldest idea in this video and I do not want to rush past it. On this planet, almost the worst moment of a person's life is survivable, in large part because someone can reach them. Not always in time, not always successfully, but the possibility is there, woven so deeply into how we live that it is invisible. You call someone. Someone comes. It is the background assumption of an entire species that has never lived anywhere else. At Jupiter, the nearest competent, willing, well-equipped assistance is 33 minutes away in one direction and 33 minutes back. Which means that for anything that happens faster than an hour, a fire, a pressure loss, a medical crisis, a control failure during a burn, the help does not arrive late. It does not exist. There is nothing to arrive. Not, you are alone out here, in the poetic sense. Alone as an engineering constraint, written into the design documents, planned around from the beginning. And notice that this is not a technology problem. Every other obstacle tonight has been, at bottom, a resource question. More fuel, more shielding, more power, more money, and enough of any of them would eventually move the number. This one does not move. A better radio does not help. A larger antenna does not help. A wealthier civilization with a 1,000-year head start on us would face precisely the same delay, because the delay is not in the equipment. It is in the space between. Every species that ever tries this, anywhere in the universe, discovers the same thing at the same distance. Past a certain radius from home, you are on your own, and no amount of caring changes it by a single second. There is a second, quieter limit stacked on top of the first, and it is about listening rather than talking. Every deep space mission humanity operates. Everyone from every country that has one is heard by the same small set of ears. The deep space network is 3 antenna complexes, one at Goldstone in the California desert, one outside Madrid, one outside Canberra. They are spaced roughly a third of the way around the planet from each other, so that as the Earth turns, at least one of them is always facing any given patch of sky. That is the entire arrangement. 3 sites, a handful of large dishes each, listening to everything we have ever sent beyond the moon. Which means time on them is rationed. A spacecraft does not simply call home when it has something to say. It is allocated a window, weeks or months in advance, negotiated against every other mission that wants the same dish on the same day. A flyby gets priority. A cruising spacecraft with nothing urgent to report gets whatever is left. And the signals they are straining to hear are almost unbelievably faint, because radio spreads out exactly the way light does with the square of the distance. The power arriving at those dishes from a spacecraft in the outer solar system is measured in fractions of a billionth of a watt. The standard comparison, and it is not an exaggeration, is that the total energy collected from decades of deep space transmissions would be insufficient to light a small bulb for a moment. And you can see that planning in how missions are actually built. The famous phrase is the 7 minutes of terror, coined for Mars landings, and it names exactly this problem. The sequence of entering the atmosphere, deploying a heat shield, releasing parachutes, firing retro rockets, and touching down takes about 7 minutes. At typical separations, the one-way signal delay is longer than that. So by the time the first indication reaches Earth that the vehicle has begun entry, the vehicle has already landed or already crashed. The event is over before the news of its beginning arrives. Everyone in the control room is watching a recording of something that has already been decided, and there is not a single thing anyone can do except wait to find out which recording they are watching. Every landing on Mars has been performed by the spacecraft itself, alone, following instructions written months earlier by people who had to imagine every way it could go wrong in advance. New Horizons makes the same point at the far end of the ladder, and makes it beautifully. That spacecraft launched in January 2006 and spent 9.5 years falling toward Pluto. It left Earth faster than anything ever had, about 16.26 kilometers per second, and it still needed a gravity assist from Jupiter and nearly a decade of coasting. The encounter itself, the reason for all of it, lasted hours. And during those hours, the spacecraft could not talk to us at all. It has one antenna, and it is fixed to the body, so pointing the instruments at Pluto means pointing the antenna away from Earth. The team on the ground made a choice: take the data or stay in touch. They took the data. So the machine went silent, executed a sequence written years earlier, and nobody on this planet knew whether it had survived the encounter until a scheduled signal arrived hours afterwards. Then it had to send everything home. And the signal from 4.5 light hours away, spread across all that distance, arrived so faintly that the data rate was down around 1 to 2 kilobits per second, slower than a telephone modem from the 1980s. Returning the full set of observations from that one flyby took roughly 15 to 16 months. 9.5 years to get there. A few hours of work. 16 months to describe it. I think that is the cleanest single illustration of what this whole video is about. The journey is not the small part of the trip. The journey is almost the entire trip, and the arrival is a rounding error at the end of it. So we have collected the 7th payment, and it is the one that cannot be engineered away by anybody, ever, at any budget. The speed of light is not a limitation of our radios. It is a property of the universe, the same for every civilization anywhere, and it means that beyond a certain distance from home, everything that happens to you is yours alone to solve. And we are still not at the edge of this. Everything so far has happened in sunlight, thin sunlight, at Jupiter, but sunlight. There is a great deal of solar system past Jupiter, and out there the light finally gives up entirely, and the answer to that turns out to depend on something so scarce that the whole reach of our species is currently limited by an amount you could hold in one hand. Somewhere in Tennessee there is a reactor, and inside it, in small quantities, a country is manufacturing the reason it can reach the outer solar system at all. I will come back to that. First, I want to take you somewhere, because the numbers in this part only make sense if you have stood in the place they describe. Imagine you are on the deck of something at Neptune's distance from the Sun, 4.5 billion kilometers out, 30 times further from the Sun than you are tonight. Your feet are on metal. There is nothing else around you in any direction. Look up and find the Sun. It is there. It is unmistakable, and it is still by far the brightest thing in the sky, and you cannot look at it directly, it would hurt, the way a welding arc across a workshop hurts. But it is not a disk. There is no circle up there with an edge you could trace. It is a point. A single, savage, white point of light, no bigger to the eye than a bright star. Hold your hand out over the deck, and it casts a shadow. A sharp one, actually sharper than a shadow on Earth, because a point source gives cleaner edges than a disk does. So there is your hand, and there is its shadow, crisp on the metal, thrown by a star. And you feel nothing. No warmth on your skin, no heat on the back of your neck, nothing at all. The light arriving there is about 1/900th of the light arriving through your window tomorrow morning. And the temperature around you, out where Neptune actually is, sits somewhere near -214 degrees Celsius. That is noon. That is the middle of the brightest part of the day at Neptune. Now, here is what I want you to notice about it. Way back near the start of tonight, at Mercury, I described the Sun as a furnace, filling 1/3 of the sky, the dominant physical fact of the place, unavoidable, so intense that a spacecraft has to be built around surviving it. 10 times the light we get here. Same star. Same object, unchanged, doing exactly what it has always done. And at one end of the solar system, it is the thing you must be protected from, and at the other end, it is a very bright star that gives you nothing, and your hand's shadow on the deck is the only evidence you have that it is more than decoration. Nothing about the Sun changed. Only the distance did. Let me give you the ladder, because it is short, and it explains everything that follows. Relative to the sunlight here on Earth, at Jupiter, about 1/27th. At Saturn, about 100th. At Uranus, roughly 1/365th. At Neptune, about 1/900th. Past Jupiter, sunlight is no longer a power source. It is scenery. It is worth putting those fractions into something you have actually experienced, because they sound abstract, and they are not. At Saturn, 1/100th of Earth's sunlight is roughly the light level of a well-lit room in the evening, perfectly adequate for seeing, hopeless for generating power. At Uranus, 1/365th is somewhere around deep twilight, the light about 40 minutes after sunset, when the color has drained out of everything, but you can still walk without stumbling. And Neptune's 1/900th is dimmer still, roughly the light of a full moon multiplied a few hundred times, which sounds like a lot until you remember how little you can do by moonlight. There is nothing wrong with any of those light levels for a camera with a long enough exposure. There is everything wrong with them for a solar panel. And there is a cruel second effect underneath the first. Cold is not the absence of a problem. Cold is a problem that consumes power. Everything on an outer planet spacecraft has to be kept warm enough to function. The batteries, the propellant lines, the instruments, the moving parts of any mechanism. Out at Neptune's distance, a spacecraft is radiating heat away constantly into an environment 200 degrees below zero, and every watt it loses has to be replaced. So the power demand rises exactly as the power supply collapses. So how do you run a spacecraft out there? You carry your own heat, and the only practical way anybody has found to do that is a radioisotope thermoelectric generator. The principle is almost crude in its simplicity. You take a material that is intensely radioactive in a specific, well-behaved way, plutonium-238, and you let it decay. Decay produces heat. Quite a lot of it. A pellet of the stuff glows a dull red from its own warmth, sitting in a room doing nothing. You surround that heat with thermocouples, which produce a small electrical current whenever one side is hotter than the other, and you point the cold side at space. There are no moving parts. Nothing to wear out, nothing to jam, nothing to lubricate. It simply gets warm and produces electricity, quietly for decades. Plutonium-238 has a half-life of about 87.7 years, which is almost perfectly chosen for the job long enough to keep working across a mission that lasts a generation, short enough to be genuinely hot while it does. It powered Voyager, Galileo, Cassini, New Horizons, Curiosity, and Perseverance. Every machine we have ever operated in the outer solar system has run on it. There is no alternative. And here is where the story stops being about physics and starts being about a supply cupboard. The United States stopped producing plutonium-238 in the late 1980s. For a quarter of a century, everything flown ran on a stockpile, an inheritance gradually spent from an era with different priorities. Production restarted at Oak Ridge National Laboratory in 2013 at a rate of about 50 grams per year. 50 grams. That is the weight of a small egg. Automating parts of the process has pushed that toward about 400 grams annually, and the laboratory's stated capacity, using its high-flux isotope reactor together with target irradiation at a second facility in Idaho, is up to around 700 grams a year. The Department of Energy's target is an average of 1.5 kilograms per year. And a single modern generator, the kind that would power a flagship mission to the outer planets, uses several kilograms of plutonium oxide. Cassini carried about 33 kilograms of it across 3 generators. In June, the Department of Energy completed a shipment of 550 grams, and the description that came with it is the most quietly astonishing sentence in this entire video. 550 grams was described as nearly enough to fill a coffee cup. A coffee cup. That is a meaningful fraction of a year of national production of the only substance that makes the outer solar system reachable. Not a warehouse. Not a stockpile in a vault. A cup. The reach of an entire civilization, past the orbit of Jupiter, is currently metered out in a quantity you could hold in one hand and would not spill. There is a natural question at this point, which is, why not simply use a reactor? A small fission reactor could produce far more power than any radioisotope generator, and the fuel for it is not scarce in the same way. The answer is that nobody has flown one on a planetary mission, and the last American reactor to operate in space did so in 1965. Designs exist, and small reactor programs have been developed and ground-tested. None of them has yet been trusted with a mission that cannot be repaired. Nor is the isotope route free of friction on the ground. The launches of Galileo, Ulysses, Cassini, and later Perseverance all drew organized public protest, specifically over the plutonium on board, and the accident analyses that accompany those launches run to hundreds of pages. The generators are built to survive a launch failure intact, and that has actually been tested by events. When a weather satellite failed shortly after launch in 1968, its generator was recovered from the ocean, found undamaged, and reused on a later mission. And once it is aboard, it starts running down immediately, because that is what a decaying isotope does. New Horizons is the clearest example. Its generator produced a little over 200 watts of electricity at launch. In 2006, sources give slightly different figures depending on whether they are quoting the beginning of the mission or the beginning of the tests. Hardware's life, so treat the exact number gently. What is not in dispute is the direction. It declines by roughly 3.5 watts every single year, as the plutonium decays and the thermocouples themselves slowly degrade. There is no refueling. There has never been a refueling. Every outer planet spacecraft ever launched has been running down a battery that began discharging the day it was assembled, and the scientific lifetime of the mission is written in advance into the half-life of a metal. You can watch this play out in real time with the Voyagers. Both have been shedding power continuously since 1977, and the mission has been managed for decades as a slow, deliberate sequence of amputations, instrument by instrument, heater by heater, switched off one at a time by a small team on the ground, making very careful decisions about what the remaining watts should be spent on. The machines are not failing. They are being gradually simplified, on purpose, so that whatever is left can keep going a little longer. So the 8th payment is on the table, and it is the strangest of the lot. Out here, past the light, the price of the journey is not fuel and not time and not risk. It is a supply of a specific isotope that one country produces by the coffee cup in a reactor, at a rate that has nothing to do with rockets or ambition or funding for spacecraft. That constraint has consequences, and they are not hypothetical, and they are not decades away. They are already reshaping the single highest priority mission in planetary science, and it is the mission that finally makes the phrase on the thumbnail of this video stop being a figure of speech. There is a photograph of Neptune that you have almost certainly seen. Deep blue, faintly banded, with a dark oval storm sitting in the southern hemisphere like a bruise. Everything you have ever seen of Neptune from close range was taken during a single pass over a matter of hours, on the 25th of August, 1989, by a spacecraft that had launched 12 years and 5 days earlier and was never coming back. There is a detail about that photograph which I think is quietly extraordinary. The dark oval, the great dark spot, an enormous storm system in Neptune's atmosphere, was one of the mission's headline discoveries. When the Hubble Space Telescope looked at Neptune again in 1994, 5 years later, it had gone. Vanished completely. So the most famous feature of that planet exists only in 12-year-old data returned by a machine designed in the early 1970s, and nothing since has ever been close enough to replace it. The same pass gave us Triton, Neptune's large moon, and found geysers on it, plumes of nitrogen erupting several kilometers up from a surface at around -235 degrees Celsius, one of the coldest places ever measured anywhere. That is also 40-year-old data from a single afternoon. And Voyager 2 only got there because of a coincidence in the calendar. Jupiter, Saturn, Uranus, and Neptune fell into an alignment in the late 1970s that let one spacecraft chain gravity assists from each in turn, an arrangement that comes around roughly once every 175 years. The Grand Tour did not happen because the technology finally arrived. It happened because a window opened and a small group of people noticed in time and got something built and launched before it shut. The next opportunity of that quality is not in anybody's lifetime. That is where we are with the ice giants. One visit each. In passing, nearly 40 years ago. I want to lay the cruise durations out now, in order, because the sequence is the argument, and I do not think it needs any decoration from me. To Jupiter, if you want to stop there. Galileo, about 6 years. Juno, about 5. Europa Clipper, 5.5, launched October 2024, arriving April 2030. To Saturn, Pioneer 11, about 6.5 years. Cassini, launched in October 1997, arriving in July 2004, 7 years of cruise, borrowing speed from Venus twice, then from Earth, then from Jupiter, to get there at all. It then worked in the Saturn system for 13 years. To Uranus and Neptune. Voyager 2, launched on the 20th of August, 1977. Uranus, in January 1986. Neptune in August 1989. 12 years. To Pluto, New Horizons, launched January 2006, closest approach on the 14th of July 2015. 9.5 years for a flyby. To Titan, Dragonfly, a rotorcraft that will fly through Titan's thick atmosphere, was formally confirmed in 2024 with a total life cycle cost of $3.35 billion and a launch date of July 2028. It arrives at Titan in 2034. 6 years of cruise, following a development program that had already absorbed multiple replans, close to $1 billion of cost growth, and more than 2 years of schedule slip before a single component of it left the ground. And a cruise of that length is not a period of waiting. Things happen in it, and sometimes the mission has to be rebuilt while it is already in flight. Galileo's main antenna, the large dish it was supposed to use to send everything home, failed to open properly after launch. The ribs stuck. Every attempt to free it failed. So the team spent much of the 6-year cruise redesigning the entire data strategy around the small backup antenna instead, writing new compression software and transmitting the fix-up to a spacecraft that was already halfway to Jupiter. The mission that arrived was not the mission that left. Cassini's cruise carried a passenger too. The European-built Huygens probe bolted to its side for 7 years, switched off, waiting. It separated in December 2004 and descended to the surface of Titan on the 14th of January, 2005, the most distant landing anyone has ever performed. It transmitted from the surface for about 90 minutes. 7 years of travel, 90 minutes of standing on the ground. Now, hold all of those in your head at once and look at what they have in common. Not one of them is a trip. Every single one is a substantial fraction of a working career. And now the mission that makes this unavoidable. Every 10 years, the planetary science community in the United States goes through a formal process to decide what matters most. It is called the Decadal Survey, and it is not a wish list. It is the document that shapes what actually gets built for the following decade. In the survey covering 2023 to 2032, the highest priority large mission, the top of the list, was an orbiter and atmospheric probe for Uranus. The reasoning is good. We have been to Uranus once, briefly, in 1986. Ice giants appear to be the most common type of planet in the galaxy, and we have never studied one properly. There is a strong case that this is the single biggest gap in planetary science. The recommended plan was: begin development in 2024, launch in 2031 or 2032, use a gravity assist at Jupiter, and arrive at Uranus in 2044 or 2045. 13 years of cruise. On the good trajectory. With the assist. That plan has already slipped. 2 things pushed it. The first is the plutonium supply we just spent the last part on. There is not enough of it produced quickly enough to fuel the generators on that schedule. The second is simply the funding profile. The money to develop the spacecraft on the recommended timeline was not there. And the Jupiter window does not wait for anybody. That gravity assist is available only when Jupiter is in the right part of its orbit, and Jupiter takes about 12 years to go round. Miss the window, and the trajectory has to be flown without the assist, which means a substantially longer cruise. Estimates published in the aftermath of the survey have put arrival on some of the less favorable routes as late as 2053. I want to translate that out of mission planning language and into human terms, because that is where it belongs. Suppose a propulsion engineer joins that project at the beginning of development at 30 years old. If the recommended schedule had held, they would have been somewhere in their early 50s when the spacecraft arrived a long wait, but a career-shaped one, with time on the other side to work with the data. On the slipped schedule, they are in their 60s. On the least favorable trajectory, they are approaching 80. The person who writes the science case for that mission will very likely not be the person who reads the results. The graduate student who will build a thesis out of the first closed data on Uranus is currently somewhere in a school being taught something else. There is also a strange institutional consequence buried in the decadal process itself. Because the community formally sets its priorities once every 10 years, a mission that does not make the cut in one cycle can wait a full decade for its next serious hearing, and then, if it is selected, wait another decade to be built and another to arrive. The decision-making machinery runs on the same generational clock as the spacecraft do. And this is not new. It is only newly visible. Cassini was first seriously proposed in the early 1980s. It ended in September 2017. 35 years, start to finish. People joined that project, young and retired inside it. Some of the original team did not live to see the end of the mission they had spent their working lives on. The Voyagers have now been operated continuously since 1977, approaching half a century, the longest continuously running spaceflight program in history, by a team that has turned over completely, more than once. There are people flying those spacecraft today who were not born when they launched. Remember what I said in the first part. You do not travel to a planet. You fall past where it is going to be. I gave you that as a fact about orbital mechanics, and it was one. But look at it again now, with 12 years in it, and 13 and 35. The falling is not a maneuver. It is not a technique. It is a duration that people live inside, going to work, having children, growing older, retiring while a machine they built continues quietly falling somewhere out in the dark, doing nothing, arriving at nothing, for years, on their behalf. That is the 9th payment, and it is the one that finally leaves the spacecraft entirely. The outer solar system does not charge the traveler, because there is no traveler. It charges the people on the ground, in the only currency any of us actually has. And that raises the question this whole video has been walking toward, which is not really a question about physics at all. What is it like? What does it actually take to spend your working life on something you will not be there to see finish? Early in the morning of the 15th of September, 2017, a room full of people in California stood watching a line on a screen. It was a signal strength plot. A single trace, running left to right, steady. It was coming from Cassini, and Cassini was at Saturn, and Cassini was falling into the planet. Here is what made that room strange, and it is the reason I have saved this for the end. Saturn was about 83 light minutes away that morning. So the signal on that screen, steady, arriving, perfectly healthy, had left the spacecraft an hour and 23 minutes earlier. Which meant that for the last hour and 23 minutes, everyone standing in that room had been watching a machine that no longer existed report that it was fine. It had already burned. It had already come apart in the upper atmosphere of Saturn, thrusters firing to hold the antenna pointed at Earth for as long as it could, and it had been gone for well over an hour. But the news of it was still crossing the solar system, and would keep arriving until the last of it had passed. They stood and watched it. Nobody in the room could do anything except wait for a thing that had already happened to finish arriving. And then the line dropped, and it was over. And it is worth knowing why it happened at all, because the reason connects directly to everything we have collected tonight. Cassini was not broken. Its instruments still worked. What it was running out of was propellant, the maneuvering fuel used to adjust its orbit and keep its antenna pointed, and its generators had been declining for 20 years, exactly as we described in the last part. Once the propellant ran out, the spacecraft would still be there, still in orbit around Saturn, but no longer steerable. And an unsteerable object in the Saturn system is a problem, because Cassini had found something during those 13 years that nobody expected. Plumes of water, vapor, and ice erupting from the south pole of the small moon Enceladus, coming from a global ocean of liquid water underneath its shell. So the mission had discovered a place that might, conceivably, support life, and had then to guarantee that its own hardware assembled on Earth, carrying whatever Earth organisms survived the journey, could never fall onto it. The answer was to use the last of the propellant deliberately. They spent the final months flying a series of increasingly audacious orbits that threaded between the planet and the innermost ring, a region nobody had ever flown through, chosen partly for the science and partly because it was on the way down. And then they aimed it into Saturn, so that the whole thing would be taken apart in the upper atmosphere and turned into a scattering of atoms mixed into a gas giant. The last image Cassini sent was of the place on the night side where it was going to enter. I want to sit in that room for a moment, because of who was in it. Cassini was first seriously proposed in the early 1980s. It launched in October 1997. It arrived at Saturn in 2004. worked there for 13 years, and ended that morning in 2017. From the first serious proposal to the last signal is about 35 years. 35 years is not a project. 35 years is most of a working life. People joined that mission in their 20s and stood in that room in their 60s. Careers began and ended inside it. Children were born to people whose entire professional identity was a spacecraft at Saturn, grew up and left home while it was still flying. And some of the people who conceived it, who fought for it, who did the early design work in the 1980s, did not live to see the morning it ended. They knew, when they started, that this was possible. That is the part I keep coming back to. Nobody who signs on to a mission like that is confused about the arithmetic. You can count. You know, on the day you accept the job, roughly what year the data will come back, and roughly how old you will be, and you do the work anyway carefully, for decades, on something whose entire purpose is located on the far side of a weight you may not clear. And this is not a rare and heroic exception. It is the ordinary condition of outer solar system exploration, and it has been for 50 years. The Voyager team is the clearest case. Those two spacecraft launched in 1977, and they are still being operated today by a small group of people at the same institution. That is approaching half a century of continuous operation, the longest-running spaceflight program in history. The team has turned over completely, more than once. There are engineers flying those spacecraft now who were not alive when they left the ground, using systems designed by people they never met, reading documentation written in a decade they have only heard about. And they are not maintaining a monument. They are making real decisions, right now, about which of the last few instruments should keep receiving power, knowing that every choice shortens something and extends something else. It is a relay, and the batons keep being handed over, and the runners keep changing, and the thing being carried has never stopped moving outward for a single day since 1977. There is a specific texture to that work which I think is worth naming. Operating Voyager today is not glamorous. It involves reading 40-year-old engineering documents, some of them on paper, written by people who assumed a level of shared context that no longer exists anywhere. It involves working out what a particular command actually does by reconstructing the logic of a computer with less memory than a modern doorbell. When something goes wrong, and things do go wrong, at increasing frequency, now the diagnosis has to be made across a round trip of more than a day and a half, using instruments that were designed before the personal computer. And every year, the team has to decide what to switch off next. There is not enough power to run everything, and there will be less next year, and less again the year after that. So somebody sits down and decides which heater can be allowed to go cold, and which instrument has produced enough data, and how many months that buys. Those are not maintenance decisions. They are decisions about what the last years of two machines should be spent on, made by people who inherited them. Now look forward instead of back. If the Uranus orbiter flies, the same thing happens again, and this time we can watch it happen from the beginning. The person who designs its power system in their 30s will be well past retirement when the first close images of that planet come home. The instrument team who spend a decade building a camera will hand it to a spacecraft, and the spacecraft will spend the following decade or two falling, and by the time it opens its eye at Uranus, most of the people who built it will be reading about it in the news, like everybody else. And the scientist who does the real work with that data, who spends 5 years understanding what an ice giant actually is, and changes what we know is at this moment somewhere in a classroom, aged 9 or 10, being taught long division, with absolutely no idea that a job is being built for them by strangers. I do not find that sad. and I want to be careful here, because it would be easy to make it sound sad, and I do not think it is. Human beings do this. We do it more often than we notice. Somebody plants an oak in a garden they will not sit under. Somebody spends 30 years on a cathedral with a spire nobody alive has seen finished. Somebody writes a law, or a piece of music, or a translation of something, knowing perfectly well that its usefulness is located somewhere past their own attendance. What is unusual about interplanetary exploration is only that we have not built any language around it. Nobody announces these missions as generational undertakings. They are announced as flights, with a launch date and an arrival date in a press release, as though the same person will be at both ends of it. And then it quietly becomes a relay anyway, and the handoffs happen in the most ordinary ways imaginable. Somebody retires. Somebody is hired. A name changes on a document. A photograph of a team from 20 years ago gets moved to a different wall. There is no ceremony for it. It just happens, over and over, in office buildings, and the machine keeps falling. So the room in California that morning was not really watching a spacecraft die. It was watching the end of a stretch of their own lives, arriving 83 minutes late, on a screen, as a flat line. And at the same moment, in the same buildings, other people were already at the start of the next one, writing the science case for a planet they will not see up close, sizing a power system for a machine that will arrive somewhere in the middle of the 21st century, doing entirely ordinary work on an entirely ordinary Tuesday for the benefit of a person currently in primary school. Which brings us, finally, back to the question we started with 2 hours ago, and to the answer I have been holding back all night. Why is the journey to each planet scarier than you think? What is actually being taken? Put your hand back on that flat surface, if it has moved. The table, the desk, the arm of the chair. The same one from 2 hours ago. It is still. It is still holding position, patiently, exactly where you left it. And the 30 kilometers per second underneath it has not paused for a moment while we talked. Here is the answer. The first layer of it is the simplest, and it is just the list. Every world charges, and every world charges in a different currency. Mercury charges energy because getting closer to the sun means giving up the sideways speed that keeps you away from it. And there is no downhill anywhere in this system. 8 years of falling and 9 billion kilometers to reach the planet next door. Venus charges the arrival. It gives you the cheapest crossing anyone has ever flown, 110 days, and takes it all back at the far end in 127 minutes. Mars charges the option to change your mind. A door that opens for a few weeks every 26 months, 500 days standing still on the far side of it, and no version of the plan in which anybody comes home early. The cruise charges cells 1.8 millisieverts a day, every day, in a currency the body does not refund, from particles that were accelerated by a dying star before the sun existed. The body charges itself, quietly, from the first 4 hours, in bone and vision and muscle and sleep. Jupiter charges electronics, one atom at a time, in a field so violent that the only workable answer anybody found was a titanium room. The distance charges the possibility of help, not slowly, not expensively, but completely, past a radius where the loop can no longer close. And, past the light, the outer system charges power and warmth, and finally, a scarce metal produced by the coffee cup in a reactor in Tennessee. That is the first layer, and if that were all, this would just be a difficult list. Here is the second layer. Every single one of those currencies converts into the same one. The energy cost is a function of the trajectory, and the cheap trajectories are the slow ones. The abort exists or does not exist, depending on how long the alignment takes. The radiation total is a rate multiplied by days. The bone loss is a percentage multiplied by months. The electronics degrade with exposure, which is exposure over time. The plutonium runs down on a half-life. Even the help the loop that will not close fails because the message takes too long. Nothing out there charges by the kilometer. Distance is free. Distance never cost anything, and that is why the diagram on the classroom wall, with its dotted line and its arrow, is not just inaccurate, but pointed in completely the wrong direction. It measures the one thing that is not for sale. The solar system does not defend itself with danger. It defends itself with duration. And duration is the one currency a human being holds a fixed and non-renewable amount of. Now, I want to be fair to the future before I finish, because none of these numbers is a law. They are consequences of the propulsion we happen to have, and propulsion can change. Nuclear thermal propulsion, heating hydrogen in a reactor and throwing it out the back, is roughly twice as efficient as the best chemical engines, and it would cut a Mars crossing from around 200 days towards something nearer 130. That is a meaningful reduction in dose, because dose is a rate. The engines were built and successfully ground tested in the 1960s before the program was cancelled, and the most recent attempt to demonstrate one in orbit was itself cancelled in 2025. Nuclear electric propulsion, a reactor running ion thrusters, is the most credible route to shortening the outer planet cruises, because it can push continuously for years, and, crucially, can decelerate for as long as it accelerated. Aerocapture, using a planet's own atmosphere to shed arrival speed instead of propellant, is probably the single most valuable technology nobody has yet flown at another world. And spinning a habitat to produce artificial gravity would deal with the bone and the eye directly, and requires no new physics at all, only a structure large enough. Every one of those is real, and several of them will probably happen. And not one of them changes the light time. Not one of them opens the door to Mars more often than every 26 months. Not one of them makes an iron nucleus traveling at 9/10 of the speed of light stop being an iron nucleus. Faster is genuinely better, because less time out means less of everything that accrues per day. But faster is not safe, and the improvements that would matter most are the ones that keep being cancelled, deferred, or never flown. Which brings us to the third layer, and the thing I have been holding back since the first sentence tonight. If you are a person, the price of this passes the value somewhere between Mars and Jupiter. Not because of rockets. The rockets could be improved. It is because of dose that accumulates at a fixed rate, and a body that begins disassembling itself on day one, and a distance at which help stops being a thing that exists, and all three of those get worse the longer you are out, and everything past Mars takes years. So it takes a lifetime. Everybody understands that sentence to mean a warning about the future. Something we will face if we ever try. Something waiting for us. It is not in the future. It has already been true for 50 years, and it has been true in a way almost nobody says out loud, and it is not the traveler's lifetime that gets spent. Every single outer planet mission our species has ever completed was finished by people who did not begin it. Voyager 2 launched in 1977 and is flown today by engineers who were not born then. Cassini ran 35 years from proposal to plunge, and some of the people who conceived it did not live to see the morning it ended. If the Uranus orbiter flies, the person who designs its power system will be past retirement before it opens its eye, and the scientist who will actually understand what an ice giant is 9 years old right now and being taught long division. That is the answer. The journey to each planet is scarier than you think, and it is scarier not because of what is out there, but because of what it costs here, and because of who pays. It takes a lifetime, just not necessarily yours. I said at the start that I would take the flat surface away from you, and I have, so let me give it back before we finish. Tomorrow morning the sun will come up outside your window. It will be a disk, a comfortable size, the size it has been your whole life, and it will warm the side of your face if you stand where it falls. That is the same star that fills a third of the sky at Mercury and burns a spacecraft's shield for 8 years. It is the same star that is a very bright point at Neptune, throwing a sharp little shadow of a hand onto a deck and giving no warmth at all. One object. Nothing about it changes. Only where you stand. And tonight, while you sleep, there are machines standing in all of those places. Bepi Colombo is falling into the furnace, about 100 days out from the end of an 8-year descent. Europa Clipper is on its way back to us, and it will pass by this planet in December, quietly, on its way to a place it will not reach for another 3.5 years. Juno is in the dark, inside its titanium box. New Horizons is out past Pluto, losing 3.5 watts a year. And the 2 Voyagers are still going, still transmitting, nearly half a century out, running on a decision somebody made in a meeting before most of us were born. None of them will come back. All of them are still, at this moment, doing exactly what they were told to do by people who accepted in advance that they might not be at the desk when the answer arrived. I do not think that is frightening, in the end. I think it is the most quietly remarkable thing our species does, this ordinary, unremarked willingness to begin something for somebody else to finish, and to hand it on without any ceremony at all, in office buildings, on ordinary afternoons, over and over, for 50 years. The distance was never the hard part. Sleep well.